Okay. Yeah, thanks. Hello, everyone. I'm Surud More. I'm a faculty here at IUCAA. And as part of the refresher course, uh, today I'm going to talk about introduction to gravitational lensing. Uh, this is one of this is the first of the three lectures that will be delivered on this particular topic. Um, uh, Myself and then Anuprita More, who is also um, working on this particular topic. So we'll be doing this set of three lectures. So today I will be covering introduction to gravitational lensing. Tomorrow you will hear about strong gravitational lensing from Anuprita. And then day after tomorrow, I will talk about the weak form of gravitational lensing. So the idea for today's lecture is to introduce you to this concept, give you some of the basic equations that arise in gravitational lensing, and get you familiar with what exactly is gravitational lensing. So let's start. Um, I wanted to first of all show you this kind of picture, which you may be used to. If you have gone to a house of mirrors or something, where you have these mirrors which have different types of curvature, and if you look at them, you see funny pictures of yourself. In this particular case, you are seeing a lady, uh, three images of the same lady, and then you can see different distortions. In one of the images, her legs are quite big, and so on. And so these similar kind of things also happen in the universe, and so um, the images that you see of objects, if they are funnily distorted in this kind of fashion, then you can try to use those images in order to learn about what is causing these distortions. So in this case here, it is mirrors. In astronomy, what causes these distortions of objects um, far, far away from us is the matter which is in between that object and us. Okay? So when you look at these kind of images, you know that in reality there cannot be three people like this, right? One which has like tall legs, another one which has a taller chest, and so on, right? So there must be something even more fundamental happening. So in this case, we know that it is an ordinary human being who is standing in front of these three mirrors. And so there are multiple phenomena that you are seeing here. So let me tell you about each of these phenomena. First is the formation of multiple images of the same object, right? Because the light coming from this person, it is going to this mirror surface, and it's that light is getting reflected and then coming towards you. Similarly, the light from this girl is also going to this particular mirror, and then it's again reaching you, right? So light is taking these three different paths and still coming towards you, and that's why you see formation of these multiple images in this particular case. In addition, you also see that at certain locations you see magnification or demagnification of images. Right? So you're seeing these legs getting taller and so on, and here they are getting shorter or squeezed. So you're seeing these magnification effects as well. And then the third thing that you don't really notice or perceive when you go to a house of mirrors is that light can take different paths, right, in order to reach you after reflecting from these mirrors. And so if the length of the path is different, um, for each of these images, then if there are any fluctuations or any changes that are happening in this particular lady, then you will see them first in one of the images, then the second image, and then the third image. So there are differences in the time of arrivals of each of these images as well, because light takes finite amount of time to go from the source to the mirror and then reaches, right? And so these three different properties, right? The fact that you can form multiple images, that you can have these different magnifications, and that you will have these different times of arrivals. These observed image properties, they can inform us about the curvature of the mirror, which is the physics that is causing these distortions. And so you can learn about the curvature of the mirror from these kind of images. So, as I said, similar things happen in the real universe. And here are a couple of examples, fascinating examples, I must say. So here what you're seeing are two big yellow elliptical galaxies. You must have heard about elliptical galaxies in the previous sets of lectures. So this is just a group of a couple of galaxies, and then there are a few galaxies nearby. What is interesting are these kind of arcs that you are seeing. Okay? So none of the galaxies in the real universe will look like these stretched arcs. In fact, what is happening is just the same thing as that house of mirrors. Something in reality, the gravity from these objects, it is causing the light coming from this background galaxy uh, to be deflected and curved, and its path is different. And so, what happens is its image gets distorted, and when its image gets distorted, you get the formation of these kind of arcs that you see. Similarly, here you can see another elliptical galaxy, and then there is almost a ring that this other bluer galaxy is forming. So this galaxy in reality is not circular in shape or the shape that you are seeing here. It is an ordinary kind of galaxy. It's just that the light coming from this galaxy, it's getting deflected, and then you are seeing this kind of a mirage where that galaxy is just bent into an arc like so. You can see these images, and because of the resemblance of these images to like this Cheshire cat, for example, if in Alice in Wonderland, this Ouroboros, we have different kinds of names for these fancy galaxies. Of course, they have nothing to do with it, but by using these distortions, the light that you see from these lensed features, you can learn a lot about the matter which is distributed in these objects which is causing the lensing. So in this case, the matter distributed here in this galaxy group or within this particular galaxy. Okay? So this is what is gravitational lensing. This is just manifestation of it, but it is mainly the deflection of light caused by massive objects. Now, the origins of why exactly this deflection of light happens, it goes back to Einstein. Right? So Einstein did this interesting experiment, a thought experiment, where he said, let's consider a lift, okay, which is just moving up in uniform motion, so with uniform velocity with respect to us. And then consider a light ray which enters this elevator, which at an initial point of time is this red elevator. As time goes on, it moves further and further up. And so, just to distinguish the elevator at a later point of time, I've colored it blue, and then another instant of time, I'm coloring it green. Right? And now, let's consider a light ray which is entering the lift at this particular location. The red dot here is telling you when the light is entering that lift. Okay? As seen by us, light should travel in a straight line, and so you should see the path of the light ray to be something like this. But for a person who is inside that lift, now uh, when the lift has gone to this blue position, the light ray will be at this blue position, and when the lift has gone to the green position, the light ray will be here. Right. So, with respect to an observer who is inside the lift, that person will see the light ray moving like this, right? So in an inclined manner, but nevertheless in a straight line. So if you have a uniformly moving object, then light still continues to travel in straight lines. But instead of a uniformly moving object, if you consider an accelerated a lift which is undergoing acceleration, then what you will see is that between the distance covered by this lift between this red and the blue instance, right? And the blue and the green instance, this will be different, right? So here, initially the distance covered is smaller, and then later on the distance covered increases. So there is an acceleration, a positive acceleration in the vertical direction, right? And now you can do the same exercise. Look at this light ray, right? Which is entering at the red point, then traveling to the blue, and then the green point. Now you can see that the location where the green dot was when the lift was moving with a constant velocity, now it has to move a little bit further down, right? So instead of seeing the light moving in a straight line, what you will see is that there is a slight curvature that this particular path of light ray um, experiences, right? And so, using the equivalence principle, then Einstein inferred that if this kind of thing happens in accelerated frame where light doesn't no longer travels in straight lines, then the same thing should also happen in the presence of gravity. So he said gravity needs to deflect. So in order to compute what this deflection is, he considered the metric in GR. So this is again something which you must have studied in the lectures on GR. If you look at the metric in the weak field limit, it looks something like this, where you have these particular terms which are related, which are related to the gravitational potential. Right? So there is a 1 plus 2 phi by c square, and then a 1 minus 2 phi by c square, which go in front of the standard metric, Minkowski metric that you are used to. Okay? So this is the metric in the weak field limit. So let's assume initially that we are working in the weak field limit. Then we know that light travels on null geodesics. So this ds square should be equal to 0 if you are considering light. So then in that case, you can ask, what is the relationship between the distance, dl, covered by the light and the time in which it covers that distance? Okay? So this will tell you what is the velocity of this light particle. Right? And so that number you can write it down as c prime. It is just dl square by dt square raised to half. And so what you get by plugging ds square equal to 0 in the upper equation is something which looks like this. Remember, we are working in the weak field limit, which means phi is much less than c square. So in that case, you can do Taylor expansions of this and keep only the leading order terms. And so what you will see is that the velocity of light, c prime, in the presence or when it is traveling in a metric which is given by this, it looks something like this. So it is the speed of light c times a correction factor, which is 1 plus 2 phi by c square. Now we know that the potentials are negative, and so because the potential is negative, what you will see is that the speed of light is less than c when it is traveling near massive objects. So light slows down near gravitational potential. So this is something that Einstein realized, and then he said, well, if light is slowing down near gravitational potentials, then we know that similar kind of things happen if you look at the speed of light, say in a glass medium, right? Or in a medium which has a refractive index greater than, right? So in those cases, when light rays move from a medium which has a different refractive index to another medium which has another refractive index, then you can see that there is a bending of light. Right? So he said that because of this slowing down of the speed of light, there should be a bending of light that also happens. And so this allowed him to then write out what this particular bending of light should look like. So let's look at how he derived this. So in a paper in 1911, he used a very clever technique in order to figure out what this deflection angle should be. So he used something called the Huygens principle. So if you look at a wavefront, right, and let's look at this particular wavefront epsilon. And you can see that it's a planar wavefront, so we are very far away from the source. That's what we are considering. Right? And according to Huygens' principle, each and every point on this wavefront acts as a source of further wavelets. Right? And these wavelets, if you then consider the envelope of these wavelets, then it tells you what the wavefront should look like at any other given instant. Right? And so in this particular case, you have this wavefront. And then let's consider 2 points, P1 and P2 on this wavefront. And because we know that the speed of light depends upon the distance away from that potential, because it depends upon the potential, And so the speed of light at this location should be different from the speed of light at this location. And so the new wavelets that you will get in equal amount of time, they will travel different distances. So in this case, the wavelet from P2, it will travel C2 times dt, while the wavelet from P1, it will travel C1 times dt. Now, if you want to know where the new wavefront is after a time dt, what you have to do is generate an envelope, right, of these different wavelets. And so now you can see that this wavefront here is tilted with respect to the original wavefront which was present here. What it means is if you have a differential speed of light at different locations, then you expect deflections to happen. Right? And so let's try to compute then what these deflections look like. So we know that the difference in the speeds, delta C prime, which is just C1 minus C2, that will be equal to delta C prime by delta x multiplied by delta x. Right? And then we know what is the expression for C prime in terms of the potential phi. Right? So we had written C prime is equal to C times 1 plus 2 phi by C square. So because we know what is C prime in terms of phi, you can write this down del C prime by del x in terms of the potential itself. And so what you'll get is 2 times del phi by C delta x times delta x. So this is just coming from the equation from the fact that light slows down. Right? So that's all that I'm using. Now, what we want to know is by what angle is this wavefront tilted with respect to the new wavefront, right? So this angle is just the angle P1, P2, and O, right, which is shown here. And so, if you want to figure out like how much is this thing changing, then what you have to do is to consider delta C prime times delta T, which is this particular line here, right? And then divide it by the distance between P1 and P2. Right? So you can see this delta C prime delta T, which is this distance here. And then we are dividing it by delta X, which is the distance between P1 and P2. Okay? So this delta alpha is this angle P1, P2. Okay? So you can then go through the equations, and this delta alpha then you can express by using these kind of equations in terms of the potential itself. Okay? And what you can show is that this change in delta alpha or the deflection and change in the angle of the traveling wavefront will be given by minus 2 by c square times the gradient of the potential along the x direction. So this is the derivative which is taken along the wavefront, which means it's in the direction perpendicular to the propagation of the wave. Right? And so that's what this derivative or del phi by del x in this particular context means. Right? And so if this is delta alpha, if you want to calculate what is the total deflection angle that will happen after you encounter a particular potential, then you just have to sum up these small delta alphas. Right? And so this alpha will then just be an integral of delta alpha along the path of the ray. Okay? And so you take this expression minus 2 by c square del phi by del x d delta L. You can write this down as gradient of phi perpendicular to the light path. Right? So that's what this del phi by del x becomes. Right? This delta L now becomes a dl, and 2 by c square is just remaining. So this equation represents how a light ray will undergo deflection because of the presence of a massive object, which is causing this particular potential, right? The gravitational potential. So what you can do is you can take a point mass object. You know what its gravitational potential looks like. It's just minus gm over r, and then you can take a gradient like this and carry out this particular integral. Right? So that's exactly what Einstein did in his 1911 paper. And for his particular calculation, he used the case of the sun. Okay, so he asked, if you consider a star which is far away from us, the sun is in between, and the earth is here. Now, let's consider a path of light ray which is just grazing the surface of the sun. Then you expect it to be deflected and to reach earth here. And just like you saw the different images of that particular lady, you expect that this particular star, because the light ray is now coming from this direction, you expect it to be seen in this apparent location. Right? And so Einstein worked out what this deflection angle alpha is by summing up all those small delta alpha deflections at each and every location on this spot. And once he did that, the formula that he got is this particular formula. It shows that the deflection angle is given by 4gm over c square divided by the distance itself. Okay? And the deflection is towards the deflector, in this particular case sun. And that's why if you want to express it in terms of the vector notation, you will write it down as psi, which is the impact parameter with respect to the sun. Now it is a vector divided by mod psi. Right? So when you do something like this, it means that this psi divided by mod psi square is equal to 1 over the impact parameter, so 1 over psi, but in a direction which is towards the deflector. Right? So for a point mass, he got this particular formula. So you plug in the equations, the values for the mass of the sun, the gravitational constant, the speed of light, as well as the impact parameter. In this case, the impact parameter that he considered was the radius of the sun. So when he put those numbers in, what he gets out is that the deflection should be about 1.75 arc seconds. So this is a very small deflection, but nevertheless, it's something which is measurable. And this particular formula was verified, and this is quite well known, by Arthur Eddington when there was an eclipse that happened in 1990. So what you are seeing here are images taken during the eclipse and after the eclipse of stars which were close to the sun during the eclipse. Okay? So they took an image of the stars during the eclipse so that all the sunlight was gone, and so they could take the image of these stars. And then after the eclipse was gone, after 6 months, the sun is nowhere close, and so they could take another image at that particular point of time. So they took these two images and then they tried to overlay on top of each other. So you are seeing these images overlaid on top of each other, and you can see that for every star there is a doublet, right? So there's this star, there's another star, there's this star, there's another star, and so on. This star and another star, this star, another star, right? So you're seeing these doublets, and the reason that you're seeing these doublets is because the first image is when the eclipse happened, and the second image is when there was no sun nearby, right? And so if there was no deflection at all, these two images should have lied on top of each other. But because there is a deflection when the sun is present during the eclipse time near these stars, and so these two locations are no longer coincident. You can also see that the difference between these two images is larger when you are closer to the sun than when you are further away. And so this shows that the deflection angle should be smaller as you go further and further, right? Right in accordance with the formula that Einstein had. So this gave a big boost to Einstein's general theory of relativity because it was able to explain, or it had already predicted what this deflection angle should be, and that those deflection angles were indeed observed. If you do this particular calculation in Newton's theory of gravity, then the deflection that you see is actually half of the prediction from relativity. And so it again established relativity on as the true theory of gravity, these particular experiments. Okay? So now that you know what light deflection is, let's move on to not just talk about the light deflection which happens due to stars, but also due to something else. So if you look at the paper from Einstein, he had said that the deflection angles are so small that it will be quite difficult to observe unless you are looking at objects which are close to the sun, right? Uh, like were observed by Arthur Eddington. But there was another guy, so Fritz Zwicky, he is a scientist from Caltech, and he had different ideas. He said, why are you just considering only stars? Right? Because Einstein had remarked that the chances to observe these kind of effects for stars is extremely small. So he said, you don't need to just observe stars. He said that you can use galaxies as lenses. Okay, so you at that particular point of time, in fact, people did not even know that galaxies exist beyond our own galaxy. So they used to call them nebulae. But he had studied a lot of these nebulae. In fact, he was the first one to discover dark matter in galaxy clusters. So he knew that there is a lot of matter that these galaxies and galaxy clusters have. And so he said, why are you worrying about the deflection of light happening because of just these stars, when you can also try to look for the deflection of light happening due to galaxies? And if you look at those kind of deflections, those are pretty large. And so you should be able to observe something more fundamental if you also, I mean, you can actually observe something which is much more remarkable than just these kind of lensing due to stars. And he listed a number of things that can be done. He was really an oracle or a visionary of sorts, because all the things that he listed, many of these things are things that we do right now. Right? So he said it would furnish an additional test of general theory of relativity that is being done currently. He said that it would also enable us to see galaxies which are very far away, which your ordinary telescopes cannot see. You would be able to see because of this gravitational lensing. So lensing can act as a telescope and show you images of objects that you could not have seen otherwise. Right? So this is also something which is seen or which is used actively right now. And then the third part was to figure out that there is indeed dark matter which is present in the universe. Okay? So what is gravitational lensing? Gravitational lensing is the bending of light due to the gravitational field of massive objects. There are three different forms of gravitational lensing. There is strong gravitational lensing, weak gravitational lensing, and microlensing. Okay? And we'll try to talk in this series of lectures at least about a few of these forms, so that you get to understand what gravitational lensing is and to give you a flavor of the kind of research that can be done with lensing. So let me again show you some of the images before we turn to more and more equations. So here you are seeing again a cluster of galaxies. There is this background galaxy which is getting lensed. You can see many other images also which are getting lensed. There are arcs here, arcs here, arcs here. Just like Zwicky said, this cluster of galaxies is really a good lens. It can lens so many of these background objects that you see. You can see another one. Right? So what we are going to do is to learn how to use these kind of objects in order to learn about the matter distribution within these galaxies or within this galaxy cluster. Okay? So gravitational lensing is one tool to probe them all. You can measure cosmological parameters. You can understand the connection between galaxies and their dark matter halos. You can do tests of GR. You can understand the nature of dark matter. You can do many, many things, right? All the things that I have listed here, there are research papers on it, and it is an increasingly becoming a more and more useful tool. Okay? So we have derived the deflection angle that happens because of a point mass, right? And I had also given you the formula for what the deflection angle looks like in terms of a general potential. So now let's try to understand how we can break it down. If you had a general lens model, not just a point mass, but something which is broadly distributed at a particular location, then what is the kind of deflections that it will produce? So virtually all the astrophysically relevant cases of gravitational lensing that happen, they correspond to something called a thin lens approximation. So what is this thin lens approximation? In this particular approximation, what you are seeing is the observer which is here. Then there's a source which is here, and the lens which is somewhere in between the observer and the source. So light which is coming from this source is getting deflected and then reaching this observer. Right? So what do I mean by the thin lens approximation is that the deflector which is causing this deflection, the extent of this deflector is small enough compared to the distances between the observer and the lens and the source. Okay? So this is called a thin lens approximation. If you are in this thin lens approximation, you can write down what is the deflection angle for a general lens distribution. Okay? So let us look at how you can write down this particular expression. So any distribution in the lens plane, you can divide it into infinitesimal components. So let's suppose this infinitesimal component, which is red here. So the mass of this component will be given by the surface density times this d2 psi prime, right? So the area element times the surface density. So that is what is here. So this is just the small mass element. The deflection angle that you get is 4gm by c square, which is 4g. This is d mass by c square. And then multiplied by this particular quantity, which is just telling you what is the impact parameter of this ray from this object. That's it. Right? So this formula is just the generalization of the point mass formula. That yes. Hello. Does anyone have questions? Okay, I don't see it. Okay, so this is the generalization of the point mass formula that you have for an object which has certain surface density at a particular length, right? And so you can just take this equation and calculate what the total deflection is at any given distance away from some fiducial point in this lens. So now let's try to understand something called a lens equation, which relates the location of the source to the location of the image and the deflection angle that is caused by this particular lens. So let's consider us here, sir, us sitting here on the earth, right? And let's consider a line joining the earth with the lens here. So this is this gray line that you can see here. And now consider a source which is located here. So you can draw a line from the earth to the unlensed position of the source, right? So this is not unobservable, but you can draw this particular line, and you can ask what is the angle between the source, earth, and the lens. So this angle, let's call it beta. Okay? Now the ray coming from this source, it reaches this point and gets deflected and reaches you. So the deflection angle is the path of the original ray and the path of the final ray. And so this deflection angle is just alpha, which is here. And now because the final ray is reaching you from this direction, you will see the image forming at this particular location instead of the original position of the source itself. Right? So let's call the position where the image forms to be theta. Now, once you have done this, this gives you the geometry of the gravitational lensing that is. Now, what I'm going to do is I'm going to define a new angle, which is this alpha here. And the way to relate this particular alpha with this alpha hat here is the following. You can consider the distance between this imaginary location where the image is forming and the source itself. This distance is given by alpha times the distance between Earth and the source. So ds times alpha is this distance. But this distance between the image and the source is also equal to the distance between the lens and the source times this angle alpha hat. And so you see alpha hat times dds, which is the distance between the lens of the deflector and the source, is equal to ds times alpha, which is this distance times this alpha. Right? So this new alpha, this particular angle, it's called the scale deflection angle. And it is easier to work in terms of the scale deflection. Because if you work in terms of the scale deflection angle, what you get is a very simple equation which relates the original position beta to the final position theta and the deflection angle. Right? So you get beta is equal to theta, the position of the image, minus this scale deflection angle alpha of theta. Right? So you get beta is equal to theta minus alpha of theta. So this particular equation is called a length equation. This just comes from pure geometry, nothing else. The only other thing that you have to remember is these distances. These are angular diameter distances because you use these distances to convert the angles into physical distances here in the source plane. Okay? That's all. So you have to remember this particular length equation, which relates the original position to the final position and the deflection angle, which is related to the potential of the lens galaxies, of the lens objects. Okay, then let's look at this geometry now in 3D rather than looking at in like the in a planar way. So again, you have the source plane, the lens plane, and the observer. The original object is here, and this would be the undeflected ray. This is beta, right? And then the actual ray travels to this position and then reaches you. So that's why this is theta. This is the angle at which you will see the image. If you see this particular thing as seen on the sky, it will look as if the lens is at a particular location in the plane of the sky. The source is somewhere else, the unlensed source, and the image that this source forms is at this particular location. This is called the image. If the lens was a point mass, then this image and the source and the lens are collinear. But if you have a general mass distribution which is not azimuthally symmetric, then you do not expect the source and the lens and the image to be in the same line either. So in this case, there is a vector equation, beta is equal to theta minus alpha of theta, that remains true, where you can just construct a coordinate system in the plane of the sky, and each of these components you can project them down. So theta you can project it onto one axis and the other axis, and so on. And you can write down the lens equation in vector notation, which will look something like this. So this will have two components, which was this plane of the sky. You will have two coordinates, right, which are required to describe the plane of the sky. So this is the lens equation. This tells you how to relate the position of the source, the unlensed position of the source, to the images that you see. Now, let's consider this equation for the deflection angle that we had, and then try to express it in terms of the scale deflection angle, which is this alpha theta, which is just a ratio of distances times this alpha. So I take this equation, I substitute it down here, okay? And then I do another important transformation, which is rather than using physical coordinates in the lens plane, I decide to use angular coordinates because angles are simple to measure and to use. Now, distances at the lens plane, they are related to the angles as observed by us on the lens plane with a simple equation, which is psi prime will be equal to the distance to the lens times theta. Right? And so I'm going to substitute psi prime is equal to dd times theta. Because there are two coordinates here, you get a dd square times d2 theta prime. This psi prime again becomes dd times theta prime. These coordinates again you can write it down like this. Right? So this dd square will cancel out with this dd square. All you will be left with is a single dt. Right? So this is distance to the deflector. So now you can rearrange that equation to get something which looks like this. So this scale deflection angle will be given by this 1 over pi factor, because I added in another pi here, times an integral over the plane of the sky, over angular coordinates in the plane of the sky, of the surface density divided by some other surface density times this particular factor. Okay? Now, this particular the deflection angle is dimensionless, which means if you look at this quantity, it should also have the dimensions of surface density. So indeed, if you work it out, it will have dimensions of surface density. And that particular surface density now, so this quantity here, this I will call it kappa. So this is just defined as kappa. This kappa is called a convergence, and this is given by the surface density divided by the other surface density, which is called a critical surface density. So this is the physical surface density in the plane of the lens. And then this is a critical surface density, which is just made up of some constants. Right? So there is the speed of light here, g here, and then the distances to the source, distance between the lens and the source, and then the distance to the lens. So these are just geometrical factors which make up the critical surface density. So if you want to work out what is the scale deflection angle, you need to know what is the surface density divided by or relative to the critical surface density. Okay? And that gives you convergence. If you just know this quantity, then you can calculate what the deflection angle is at any given location of the image. And if you know the deflection angle at any given location of the image, you can work out where the original position of this observed image should have been using the lens equation. Now, this lens equation seems complicated, right? Because you have to do this kind of vector manipulations and integrations, which are written in a vector form, right? This alpha of theta is 1 over pi, then integral of this quantity. So it turns out that instead of having to work with these kind of vector quantities, you can also work with a scalar potential, which is psi here. It is defined according to this relation. So if you define your lensing potential like this, and now you just take a simple gradient of this lensing potential, then it turns out that it gives you back this vector scale deflection angle. Okay? So the gradient of psi, and remember, this psi is defined in the plane of the sky because it is just a function of this theta, right? And so when you take the gradient, it is in 2 dimensions in the plane of the sky in angular coordinates, right? So that's how you will take the gradient. There's theta 1, theta 2. So you have a del theta 1 by del psi by del theta and del psi by del theta. So that gives you 2 components of the deflection angle. Now that you have this deflection angle, what you can also do is take the divergence of this deflection angle. It turns out if you take the divergence of this quantity, then you can show, so this is the divergence of a gradient of this potential, which means it's a Laplacian. Right? So the Laplacian of the potential, you can show that it equals 2 times kappa of theta. So what this means is that you can actually define a potential, and there are lots of similarities with the gravitational potential that you're used to in 3 dimensions, the forces and the Poisson equation, right? So you can see similar things here. So there is a lensing potential instead of the gravitational potential. It obeys the Laplacian, a Poisson equation, right? Which looks like this. So Laplacian of psi is equal to 2 kappa. This is like the Poisson equation, but in 2 dimensions. And then if you want to calculate the deflection angle, that is the equivalent thing is the force. And so you have to take a gradient of the potential. So here you are taking the gradient of the potential itself. Right? And so this is how you can simplify some of these calculations for the deflection angles also. And the for the deflection angles and how to relate the potential to the convergence. So now you have the lens equation. The lens equation, it relates the positions in the source plane to the positions in the image. Right? This particular lens equation, it's a nonlinear equation, right? Because it's beta is equal to theta minus alpha of theta. Alpha of theta can have different forms. And so this is a nonlinear equation. For a given value of beta, there can be multiple solutions for theta. Right? So this means that you can see for the same location of the source, you can see multiple images, theta 1, theta 2, theta 3, theta 4, which still obey the lens equation. And it means that if these solutions exist, then light should take each of these paths. And so you should see multiple images of the same object. Okay? It doesn't happen all the time. If you are too far away from the deflector, then you only see one image. But as you come closer and closer and closer, these different paths open up, and you can see the lens equation developing more and more solutions. So this lens equation, it is telling you this the relationship between the images and the sources, and it gives you the reason why you see multiple images. That was the first observable, as I had said, the deflection angles. Now let's consider the second observable, which is the magnification of each of these images. Now the magnification is related to the Jacobian of the transformation between the source plane and the lens plane, right? So you can consider the lens equation, it represents some sort of a transformation given any point in the source plane. Where will it go in the lens, right? This is what the lens equation tells. So if you now want to calculate how magnified a particular image will be, then you have to take some object which has a particular area in the source plane and then figure out what is the area in as seen for the image that gets formed for this particular source. Right? And so if you divide the or if you take the ratio um, of the area of the image divided by the area of the source, that will give you the magnification. Right? So that's what we are doing here. Because it's a mapping, is theta going to beta. What we can do is consider the magnification matrix, which is given by the partial derivative of theta with respect to beta. Now remember, each theta and beta, these were coordinates on the plane of the sky, angular coordinates in the plane of the sky. So they have two components each, which means this del theta by del beta, it will have four components in total. Right? Del theta 1 by del beta 1, del theta 2 by del beta 1, and then del theta 2 by del beta 2, and del theta 2 by del beta. Right? So four components that you have for this magnification matrix. And if you want to take a look at these areas and then divide by these areas, it's just given by this determinant. Right? So the ratio between these areas will be given by this determinant. And so if you know this determinant, you can compute what the magnifications are at any given location. So let's try to understand what these magnification ratios would be. So instead of considering the magnification matrix, which is del theta by del beta, it is simpler if you consider the inverse of it. So the inverse is written here as del beta by del theta. Because there are different components, I have given labels I and j here. So del beta I by del theta j. Now remember, in terms of the lens equation, beta is equal to theta minus alpha of theta. What this means is if you take a derivative with respect to theta, here you are going to get a delta I, right? Because beta I is equal to theta I minus alpha I. Right? And so del theta I by del theta j will give you a Kronecker delta ij. Right? So it will be 1 when I is equal to j, 0 when I is not equal to j. Right? So that's the first component. And then you have to subtract alpha I, and the derivative of alpha is with respect to theta j, right? So you get del alpha I by del theta. So this quantity, you know that alpha I is just the gradient of psi, which means it is del by del theta I of psi, right? Of the potential, lensing potential psi. And so this term, you can just write it down as del 2 psi by del theta I del theta j. So if you want to work out what this inverse magnification matrix is, then its components will be given by this particular term. So the first component, del beta 1 by del theta 1, which goes here, it will look like 1 minus del 2 psi by del theta 1 square. This component will look like 1 minus del 2 psi by del theta 1 del theta 2. This one again equal. And this last component will look like 1 minus del 2 psi by del theta 2 square. So let's call it psi 2 2. Then the 1 1 component will call it psi 1 1. And then this 1 2 component will call it psi 1. Okay? So you can take the matrix which gets defined like this, and then you can express it in terms of some other variables, gamma 1, gamma 2, and then the kappa that you are using. So you know the kappa and lensing potential, they obey the Poisson equation. with 2 times kappa, right? The Laplacian of psi is 2 times kappa. And so you get this particular identity. Kappa is half times psi 1 plus psi 2. And then you can define these quantities gamma 1 and gamma 2 to be something like this. Then the inverse magnification matrix that you get based on these components, it looks something like this. So it is a matrix which is symmetric, right? So you have some value here, a different value here, but the values along the non-diagonal elements, they are exactly equal. Okay? And so you get a symmetric matrix as the Jacobian matrix for the transformation going from theta to beta. And now you have expressed it in terms of these new variables gamma 1, gamma 2, and kappa. Now, this matrix, you can separate it into 2 terms. Right? One is 1 minus kappa, 1 minus kappa, 0, 0. And the other one is plus minus gamma 1, gamma 1, minus gamma 2, minus gamma 2 in these particular conditions. So if you look at just this particular transformation, let's suppose that gamma 2 is equal to 0, gamma 1 is equal to 0. So there is none of this second term is present. What it means is if you have a circular object in the source plane, what it is telling you is that the x component gets increased in size by 1 minus kappa and the y component gets increased in size by 1 minus kappa. And so any object, it is going to be isotopically changed by 1 minus kappa, right? Because I can take this 1 minus kappa out and then you get an identity matrix. So any image that you see, any source that you have, if you look at what happens if you just apply this transformation, then it just magnifies that object by 1 minus kappa. Right? So that's the simple meaning of this first term. Now let's look at the second term. The second term, it introduces a shear on that object. Okay? So a circular object no longer will remain a circle because what is happening in the x direction is different from what is happening in the y direction. Right? And so you get a shearing effect, which is put in addition to this uniform magnification method. So what happens is if you take a source which is circular, you apply the inverse of the magnification matrix, then what you get is this particular object which looks like an ellipse. Right? So from here, you go to an ellipse. If you only had convergence, then this circle would just have stretched in all directions in equal manner, which means you would get something like these, like the envelope of these circles, right? So something like this. Instead, what you observe is this particular elliptical shape as an image. Okay? So you have a convergence, which is the uniform magnification, but in addition to that, you have shearing. Now, the direction of this shearing is related to the values of this gamma 1 and gamma 2. And if you know the values of this gamma 1 and gamma 2, you can tell exactly in which direction it will get shear. Okay? So what is happening is you can now consider lensing. What lensing is doing is taking objects. If you consider bundles of light rays or photon bundles coming from this object, these photon bundles, they are because of the convergence, their size is increasing. Size of that photon bundle increases, and then because of the shear, the shape of that photon bundle also changes. Okay? So instead of remaining a circle, now it becomes. So that was the second part. So we now figured out, if you know the lens equation, how you can write down what is the magnification at any given position or at any given image, and that is related to the calculation of the convergence and the shear that are done. Now let's look at the last thing, which is the geometric, which is the time delay. Right? I had told you that images from, so if you form multiple images, let's suppose there is one image here, and then another image which is formed because light rays can go from here to this location, then the distance traveled by each of these light rays is different. And that's why you will get something called a geometric time delay. Right? So let's first work out what is the geometric time delay. Then there is another additional thing that happens. So I will come to that. Okay? So let's consider again the lens diagram that I had shown before. So there is the observer here, the source is here. The unlensed path of the light ray is this red line. What we want to work out is what is the time delay between the path from S to O compared to the path from S to B and B to O. This is the geometric time delay because there is an increase in the geometric path, and that's why there should be an extra time which is taken for light which is coming from the source to reach us. In the absence of the lens, it would have come directly, but because the lens is present, it has introduced an extra time delay. So let's work what that time delay is. In order to work that out, what you can do is you can define isosceles triangles where SU is equal to SC. Okay, so let's suppose you define this isosceles triangle SCU and then OUA. Right? So this isosceles triangle. Then we know that these two angles should be equal. So BUO and AUO and UAO. These angles should be exactly equal because this is an isosceles triangle. And the extra path length that you have will just be equal to AB plus BC because this path, the rest of the path, CS, is same as US and AO is same as U. So the extra path length introduced is this path length here, A to B plus B to C. So then what is AB plus BC? Right? So AB plus BC is just the sum of the angles AUB plus BUC, which is just this angle here, AUC, multiplied by the distance UB. So this particular distance. So what is this particular distance BL? Right? So this distance is just the scale deflection angle alpha times the distance to the lens, so dd. Right? So it is dd times alpha. That is what this distance is. And then the angle AUC, I have just written it down again as the angle AUC. Now let's work out what is angle AUC. Now this AU, in order to do that, the first thing to notice is that the sum of the angles AUO plus AUC plus CUS is equal to 180, right? So these form angles which are with respect to this line. And so the sum of these three angles, it should be equal to 180, right? So that is AUO plus AUC plus CUS is 180. Now, what you can do is you can also use the equation that BUO plus AUO plus UAO and then AOU. This is equal to 90. Right? This is equal to 180, which means you can write down this angle AUO in terms of this angle. So that is what is done here. Because this is an isosceles triangle, you can show that this angle is 90 minus half of this angle. So that's what is written here, 90 minus AOU by 2. And then similarly here, this you can express this angle here with respect to the angle here. So that is 90 minus CSU by 2. And so once you take these this equation, then you can express now AUC with respect to these angles here. This angle here, which is just alpha, and then this angle here. Okay. So once you work it out, it turns out that you can write down this angle AUC to be half of the deflection angle times these numbers ds by dds, which is basically just the scale deflection angle, right? So this is the scale deflection angle divided by 2. This is what this angle is. It's the scale deflection. So if the deflection angle is alpha, the scale deflection angle, which is here, so this divided by 2 is this angle. So you can show that. So now that you have that, now you can ask, okay, what is the additional path length that you get? Because you wanted this angle, right? So we have worked out what this angle is. So we can substitute this equation here that we got, alpha by 2 times ds by dds in this particular equation to get the extra path. So the extra path length that you get is equal to half times alpha square times this quantity dd ds divided by dx. This alpha is the scale deflection. So this angle here. Now we also know that this angle is just theta minus beta. So you can also write down this extra path length to be half of theta minus beta the whole square times this factor. And if you want to calculate what is the extra time delay that is taken by the light ray, then you have to take this extra path length and just divide by c. So that's the geometric time delay that you get. So that is what is expressed here. There is an additional 1 plus z factor that comes in because of the cosmological expansion. But other than that, I have derived what, or in the slide actually explains how to derive this geometric time delay. In addition to the geometric time delay, there is also an extra component which comes because light is now slowing down in the presence of the potential of this object. Okay? And so you can again go through the mathematics of this time delay. The way you write it is dl by c prime, where c prime is the actual speed of light in the presence of this massive object, right? So there's dl by c prime. This will be the time taken to travel a small length element dl. And the time taken to travel, if the speed was c, is equal to dl by c. Okay? And so if you subtract it, you can also get another component for the extra time taken by light rays. And that is given by this, the right-hand side of this equation. So then you can go through the mathematics and show that this extra gravitational time delay, because of the slowing down of the speed of light, is given by this particular equation, where psi is the lensing potential that we had derived previously, times this 1 plus zd factor, which comes because of the expansion of the universe, and then these factors ds, dd, and dds that you have used. So there are two components to the time delays of images that form at different locations. One is the gravitational component, and the other one is the geometric component. So you can now take these two components and put them together to express what is the effective time delay between two different images coming from different locations, or any given image coming at a particular location compared to the unperturbed path of light. So that time delay, this time delay, is equal to some constant here, which depends upon the redshift of the deflector and some of these other distances, times a quantity called tau, which is called a Fermat potential. Now, this Fermat potential is given by this equation here. So it has the half theta minus beta the whole square. This is the geometric path time delay component. And then an extra component which is coming due to the lensing potential. This is the gravitational time delay. So if you look at this particular Fermat potential itself, you can take the gradient of this potential and equate it to 0. What it gives you back is the lens equation, which is quite interesting, right? Because what it's telling you is for a given value of beta, you can write down for all possible values of theta, what is the time delay between the unperturbed path that light can take, and if it had gone to some other theta location and come to you. So if that source had formed an image at particular theta, what would its time delay be with respect to the unperturbed light? That is what this time delay equation, the Fermat potential is telling. When you take the gradient of this potential and equate it to 0, it means you are trying to find the stationary points of this time Fermat potential surface. Then these stationary points obey the lens equation. So at the location of these stationary points of the Fermat potential, you form images. So this is related to the fact that to the Fermat theorem that you are used to in optics, where light takes the optimum path to go from location 1 to location 2, right? So in this case, what it's telling you is that light takes actually stationary paths which correspond to the stationary points of this particular Fermat potential surface, which is just the time of arrival, uh, which tells you the time of arrival with respect to the unlensed source. So if you have multiple stationary points, then you can get multiple images because light will take any of these possible paths and reach you. Okay, so in the set of these lectures, I think I'm running out of time. So in this first lecture, what I told you about is the basics of gravitational lensing. I told you what lensing is. It's coming because of the deflection of light that you see multiple images. So let me go back to the first slide that we have. Right. So you see multiple images, just like you are seeing for this lady here. I also derived the equations for magnifications, which tells you how this lady and the images that you are seeing of this lady at different locations, how they will be stretched. Right. So we derived what the magnification should look like. And the third thing that we derived is the time of arrival from each of these images. So these three quantities are the ones that we are going to use tomorrow in tomorrow's lecture. And you will see how they can be used in order to learn about the mass distribution in the universe itself and mass distributions in certain objects and how it causes multiple different images. So you will learn about all of this in the next lecture. So stay tuned for it. So I'll take questions now. I can see there is one question from Tanuj Datta. Do you want to ask this question, Tanuj, by yourself? You can unmute yourself. Tanuj? Yeah.
Yes, sir. Yes, sir. Can you please go to the slide where you explain the lens equation?
Yes. Let's see.
The first slide of lens equation.
Yeah.
Yes, sir. Here we can see that, from Earth we can see the astronomical source directly. Then why we will use the lensing technique here?
No. So when you say that you can see the source directly, what you are saying is that there is a path of light from Earth. This red line is what you are talking about, right?
Yes, sir.
But light does not take this path. Okay, so this is just an imaginary line that I have drawn. In the absence of the lens, where would this source be? Instead, what happens is light takes this circuitous path. It goes to this location and then comes to us. So it light is not able to take this particular path to come to you. Okay? So this is different from your commonly used phenomena. So suppose I have this bottle in front of me, then anything which I can see, which is not obstructed, I should be able to see, right? But if this bottle is extremely massive, then light rays come not straight way. They don't travel in a straight line, but they will curve and then come towards. So it's exactly the same thing which is happening. The actual path that light takes is not this red line, but it takes this particular path that you are seeing.
Yes,
So you
sir. I
never
get it.
see the image at this location. You never see this unlensed source at all. What you see is only the image. Okay?
Yes, sir.
Okay. Any other equations? Sorry, other questions? Yes, let me look at um, the Excel sheet where people or from the Google form. There are questions which are also asked from YouTube. So let me take that. So one of the questions is, uh, how long can a gravitational lensing stay in space? Okay, so I mean, gravitational objects or objects which are causing this gravitational lensing, these massive objects, um, it's not like they are hanging out there in space, like they are there. and then there's gravity which is acting on these objects, and then that causes these objects to move. So maybe you are trying to ask is it possible that the geometry that we are seeing between the Earth and the lens and the source, whether that can change as a function of time? Yes, in principle, it can change as a function of time. So sometimes there are objects which will come in between you and the source and then lens the source, and then they can move away from you, and then they don't cause a lot of lensing anymore, right, of this source because the impact parameter is quite large. Right? So it depends upon how quickly these objects are moving and how small an angle um, you need to be in to see detectable differences once these objects move, once the lens moves. So you will learn about something called the Einstein radius tomorrow from Anuprita. And if you have um, the angles of the source, if they change appreciably with respect to the Einstein radius of the lens, then you can see tangible differences in the positions of the sources during the time scales in which the lens moves. So these kind of things can happen in particular in the case of something called microlensing, where you have a star lensing another star, and so this star comes in front of the background star, and then it magnifies it. It causes multiple images of this star, and then as soon as it moves away, this the background star it returns to its original size. So you can indeed see some motion between the lens and the source.
Thank you, sir.
Okay. Any other question? I see there is a hand raised by Shubhadeep Datta. So let me ask you to unmute yourself.
Hello, sir.
Yes, hi.
Sir, I have a query that can gravitational lensing cause false positive, that is repeated or reflected images that's a multiple of original image. So the source looks brighter, but actually that's different. So can
Yes,
this possible?
yes, indeed. So as I mentioned, there is a magnification, right, which relates the um, positions in the lens plane to the positions in the source plane to the positions in the lens plane. There is a transformation equation between them, and that's the lens equation. If you compute the Jacobian of this transformation and take a determinant, it tells you what is the ratio of the areas in the lens plane to the ratio of the area in the source plane. This gives you actually a magnification, which means that objects which appear smaller, they appear bigger after getting lens, or they can appear smaller as well. It depends upon how big this magnification is, whether it is greater than 1 or smaller than 1. Okay? And if the magnification is larger, it means there are many more photons which are directed towards you from that particular object. And so you see the flux of this object increasing. The surface brightness stays the same because your area increases and the amount of light that you get also increases, but they increase in proportion. And that's why the surface brightness stays the same. But the total amount of light that you will get from this object also increases if the magnification is greater. So indeed, you will see objects which you could not have seen before, and you will see them with even more detail than you would have seen if you just had directly observed because of gravitational lens.
Yeah,
Okay?
thank you, sir.
Yeah. So let me see if there are further questions. Yes. So what is the utility of treating the angles as vectors? So this is from Shubrat Sarangi. Um, so the reason to treat these angles as vectors is the following. First of all, the deflection that happens because of a point mass, it is directed towards that point mass. Right? Now, let's suppose that there are 2 point masses, right? One is here and another one is here. Then the deflection that happens because of this point mass is directed towards the first point mass. Because of the second point mass is directed towards the other point mass. Right? And so the effective deflection that you are going to see, it is actually the vector sum of these two deflections. Right? So it's not that's the reason why we are treating these deflections as vectors. Okay? So if there were two objects, one here and one here, and then there was a light ray which was coming right through the middle, then just in the same manner uh, uh, that there will be a deflection towards the first mass and the second mass. But if these masses are exactly equal, these two deflections will cancel out. So deflections inherently are vector quantities. And they are directed towards that point mass. When you have an extended distribution, you have to compute all these deflection angles from each of these small mass elements and add them up vectorially. That's the reason why we are treating them as vectors. Okay, thank you. So there's another question from YouTube. Can you shed more light on the convergence kappa? Is it anyhow related to the curvature of space? Okay, so the convergence kappa, of course, is related to the surface density itself, right? So let's go to that particular equation. So the convergence kappa is related to this particular ratio, right? It's the surface density divided by this critical surface density. So it is indeed related to the surface density. Now the surface density is causing a curvature of space-time near that particular object. But perhaps you are asking whether it is related to the curvature of the space as whole, right? So, or to the geometry of the universe itself. Then that is not indeed correct because this kappa is just a local quantity. It will be related to the local curvature, not to the global geometry of it. So I hope that answers that question. So do we have any other questions? Yes. Soham Basu. You can unmute yourself and ask this question. Let me see. Go ahead, Soham.
Sir, you mentioned about 1911 paper of Einstein
Yes.
applying, I mean, dealing with the Huygens theory.
Yeah.
Was it based on relativity, sir, special relativity or general relativity?
Right. So at the time of in 1911, he did not know. I mean, he had not fully developed general relativity at that point of time, right? And so he had used an incomplete equation in order to derive the deflection angles. But what he had noticed definitely is that the speed of light does slow down near because of the gravitational potential of objects nearby. He did miss a factor of 2 in that 1911 paper because he did not have the full theory of shear. But then once you have calculated what is the speed of light, what is the difference in the speed of light in the presence of a gravitational potential, then going from there and using the Huygens principle to calculate the deflection angle, there is no problem at all. So in 1911, he used the wrong equation. He calculated the change in the speed of light because of the presence of a potential. That equation was wrong by a factor 2. Okay, so instead of 1 plus 2 phi by c square, he just had 1 plus phi by c square. And so the deflection angle he derived using the Huygens principle was half of what the full general theory of relativity is. Now, if you look at it, it is interesting because Newton's prediction is actually half of it also, right? And so, if he had not upgraded to the general theory of relativity before the eclipse of 1990, he would have gotten it wrong as well, just like Newton's theory. But between 1911 and 1919, he had developed the general theory of relativity in 1916, and he did correct for this factor of 2. And then the rest is history. Does that answer the question? Yeah, I suppose you muted yourself. So then there is one question in chat. This person's mic is not working. Soham Basu. If we see multiple images in a cluster, how do we identify the real source of an object? This is a very interesting question. So in reality, when you look at the images that you see behind the cluster, right? Many of these images are lensed, and so we never see what the real source looks like. Okay, just like if like you looked at this first, the lady on that first slide, right? You can think about an analogy like there are three of these images, and if you didn't have this picture at all, you would not know what the real image is. Right? The other thing that you want to know is whether these three images are the images of the same object or not, right? And the way to do it is as follows, right? So you look at these images and you see there are certain characteristics that these images have, right? I mean, even though there are different stretches and so on, um, in each of these images, you can see this shirt which has flowers drawn on it. You can see these jeans. You can see the slippers that this girl is wearing and so on. So you can use some other quantities of these galaxies, like the spectra taken for these galaxies, which act as like a fingerprint for these galaxies, right? Because it tells you what is the composition of that galaxy, which is getting lensed. So if you see exactly the same redshift, exactly the same spectra for each of these images, then you know that most likely this galaxy is exactly the same. The second aspect is lensing. As I said, it conserves surface brightness, right? And so, because it is conserving surface brightness, you can look at these images and ask whether the surface brightness of these galaxies is the same. So, all these things put together, it helps you to then determine whether these multiple images that you have formed, whether they are really the images of the same source. So, you will hear more about it from other people. Okay. I see one more hand, Prajakta Mane. You can unmute yourself.
Yeah, so am I audible?
Hello?
Hello. Am I audible?
Yeah, we can.
Yeah, so my question was about the image that we saw during the eclipse, the image that showed the lensed images of the stars. So that's practically a microlensing, right? Because the stars are getting lensed by a star. So why do we not see any magnification there?
No, so this is not the case of microlensing. So in microlensing, the deflection angles are typically quite small, like micro arcsecond level. This is arcsecond level lensing that you're seeing, right? So that's the first part. In microlensing, what happens is you get multiple images of the same source, but these multiple images, they are separated by such a small distance that all of these images, they actually merge together. And so they appear to be the same image. And that's why the flux increases. In this particular case, you are only seeing the deflection of the light ray. You are not even seeing multiple images of the same object. Okay, it's just there is an object which would have been there if the sun was not near, and then there's another. The actual image that you see is a little bit further away from the position where it was supposed to be. So it's not the case of microlensing. There would be certain small amount of magnification that would be caused because of this deviation of the difference that you see, but it's going to be quite small.
Okay, yeah.
Okay. Any other questions? Dibharti, do you see any other questions on YouTube?
No, I don't see any other questions.
Okay. Okay, then I guess you'll stop here. I'm sorry for running over time. We will see you tomorrow for the strong lensing.
Thank you.
Thank you.